G'day, McGrathletes. It is school holidays and it is pissing down rain outside, so what better day to make a video on mathematics? We're starting off with a warm-up question that I plagiarised from a Sydney Grammar School trial exam. We've got a 1 kilogram object moving along the x-axis with the resistive force given by this expression. Okay, bloody blah. Here is the equation of motion. So they've done the mechanics for you, set up the equation for you, which go do the maths. Initially, the object is at the origin, velocity 3 meters per second. Find v as a function of x. Okay, let's rip into it. So let's get rid of the crap and just leave some room for some maths. What we're going to do is we're going to write our equation given to us in the question. I'm going to try and go from this to a function relating velocity in terms of x. So first thing we'll do is we'll divide both sides by v to tidy things up a little bit. And now we can't integrate both sides with respect to x, but we can integrate with respect to v, which means we need to turn both sides of the equation upside down. So I'm just going to combine the right-hand side into one fraction by writing 1 as 3 over 3. So it looks like this. Now we can invert both sides and we have dx on dv, pulling the negative out of the top, which is now the bottom. And so it looks like this. This is what we are going to integrate. So if we integrate both sides with respect to v, we end up with x on the left, and on the right we have this integral. So we have something plus something squared. So we're going to be applying inverse tan, which we'll be doing again later in the video. So for inverse tan, we want a squared plus x squared with an a on the top. So because we have root 3 squared on the bottom, I would love the top to be root 3. So I'm going to split this 3 into root 3 times root 3 and chuck one of them out the front with the negative. So it looks like this. Now it's in a good position for us to do some integration using inverse tan. So we have x equals negative root 3 of tan inverse of v over root 3. Don't forget your constant. We'll use our initial conditions to figure out what the constant is. So initially, our object at the origin, so x is going to be 0, and velocity is going to be 3. So we're going to chuck that into the equation. 0 on the left, 3 for the v. Now chucking this on the left-hand side, we're going to end up with c equals, oh cool, we can actually figure this out. Yep. So 3 divided by root 3 is going to give us root 3, and then tan inverse of root 3 is going to be 60 degrees, which is pi on 3. So we're just turning this into pi on 3, putting across the left, and we get c equals root 3 pi on 3. Putting that back into the equation just up here as our constant. And now the last part of the question is just to rearrange this to make v the subject, because we want v as a function of x. Currently we have x as a function of v, so we're going to try and rearrange this. Okay, so here it is again. Let's minus the root 3 pi on 3 over to the left. Now let's divide everything by negative root 3. So we get negative x on root 3. Root 3's cancel out here, and this becomes positive. Now we're going to take tan of both sides to get rid of the tan inverse. So we'll have v on root 3 equals tan of the left-hand side, which is right here. Then we'll just multiply the root 3 across the other side, and there we have our full 3 marks answer for v as a function of x. All right, today's lesson is a super important one for the Extension 2 course. It's on resisted motion. So these questions are without doubt always in the HSC. They're always big marks. This one lesson I would expect to account for at somewhere between 5 and 10% of the HSC exam. Some of these questions involve a lot of interpretation and forming equations. Sometimes the exam will just give you the equation and ask you to do the calculus and the rearranging. So we'll do a bit of variety today. 2 types of questions. We have horizontal resisted motion and vertical. I'm going to give you 2 examples of both, but yeah, it's a massive topic, so I recommend doing some more study after you watch this video if you haven't already had some idea of this topic. So let's go on with a bit of theory. All right, situation 1 is we have a cube sliding across a table being brought to rest by a resistive force. Okay, when you slide something across the table, it stops moving because of resistance. That resistance is the friction from the table and also the impact with the air on the object. Okay, so resistive forces always act in the opposite direction to your motion. So for quite a lot of these questions, we'll be saying the way we're moving is the positive direction, and the resistance is going to move against us, which is going to be negative in terms of algebra for our equations. So here is our mass translation for this this scenario. We have force. There's nothing moving the cube forward once we let go, because it's just moving, from momentum. So there's no force moving it forward. All we have is a resistive force, which is proportional to its squared velocity moving against us in the negative direction. We can write our force, as always, as mass times acceleration, and then we can divide by mass, and then we can write acceleration in whatever form we need. For this scenario, we could be trying to find a relationship between v and x, so I use dv on dx times v. But yeah, writing your acceleration depends on what variables you're trying to find for that specific example. So we're going to do a bit of variety today, show you all the different types as best I can in 30 or so minutes. Let's see how we go. Okay, for horizontal, there's going to be two types of horizontal questions. I'm sorry, there's another horizontal. So last one, there was nothing moving us forward. We were just stopping from resistance. This one, we have something pushing us forward. We have a car driving through quicksand, push forward with a constant force of F0. That's going to be from the engine of the car. We have resistive force from the air resistance and also from the friction of the quicksand. So turn this into an equation. It's going to look like this. We have our force with the engine driving us forward in the positive direction. We've got the proportional velocity force against us, and we have the air resistance proportional to the square velocity working against us. Okay, so things pushing us forwards are going to be positive in our equations, which are usually pretty rare for these questions. Usually it's going to be interpreting stuff from the question as resistance and writing them as negative forces, and then doing a bit of funky calculus. Okay, for vertical, there's going to be two scenarios. Scenario one is where we are moving up in the air, and scenario two is going to be where we're moving down from the air. So in both these scenarios, resistance is going to work against us, which will be negative in our equations. The only difference is gravity. When we're being thrown up, gravity is working against us. When we're falling down, gravity is working with us. So if we were throwing a ball into the air, we would have our gravity force, mass times acceleration, and it's negative because it's working against us because we are moving up, gravity wants to pull us down. Air resistance always working against us, always going to be negative. If we are falling, however, like I said, gravity is working with us, so that force is going to be in the positive direction. However, the air resistance is still working against us and is always going to be a negative component of our equation. Let's dive into our first example. We have a rowing team crossing a finish line with initial speed, and then once you hit the finish line, you stop rowing because the race is over and it's time for the beers. All right, in a model, we have two drag forces. We've got the contact with the water, so that's like water friction, and we have air resistance given by this. M is the mass, X is displacement. Find V as a function of X. Okay, this is the type of question where we need to interpret the information from the words and turn them into maths. So we're going to write our force equation. It looks like this. Okay, like I said, nothing moving us forward because once we hit the finish line, we stop rowing. There's no longer a force pushing us forward. We only have the resistive forces causing us to stop. We have the water contact here, negative because it's resisting us, and we have the air resistance resisting us as well, so this is also negative. This is our starting point. Like I said, sometimes the question will give you this, or sometimes you have to make this equation yourself. Now we're trying to go from this to an expression relating V and X. So first thing we'll do is we'll write force as mass times acceleration. While I'm here, I'll combine these two into one fraction by writing this as 10 over 100 and then combining it all together, putting the negative at the front of the fraction. Now for our acceleration, because we are trying to link V and X, this is a scenario where we're going to use V dV on dx. So we're going to divide both sides by mass to get rid of the m's everywhere. Then we'll write acceleration as V dV on dx. Now we can divide both sides by v to simplify our expression a little bit. So this is going to turn into 10v and this is going to turn into 1. Now because we have dx, we can't integrate both sides with respect to x. We can integrate with respect to v. So we need to invert both sides of this fraction to have dx on dv is this upside down. Cool, now we can integrate both sides with respect to v, and that's going to get us x in terms of v, which looks like this. Here's our integral. I'm just going to write the 100 as 10 times 10 and write one of the 10s out the front because I want to integrate this using a natural logarithm, which means the top of the fraction needs to be the derivative of the bottom, which is 10. So writing it in this way just means it's going to be much easier to do some calculus with. Okay, now integrating both sides, we have x on the left, we have minus 10 times natural log of the denominator. Don't forget your constant, okay? Always going to be constants, which we'll figure out using the information in the question as per always. So from the question, we have, when we cross the finish line, which is where we are measuring from, so at the finish line, our displacement is 0, and our velocity is going to be equal to 5.5. So I'm going to sub in v for 5.5, x for 0. On the left, we have 0. We get minus 10 times log of 55 plus 1 plus c. Moving this negative across the left, we get that c is equal to 10 log 56. That's our constant. I can chuck it up here and continue with the question. Going to write the constant at the front, so we have positive and then the minus. Just looks a little bit nicer for me. And now we're almost there. We just need to rearrange this, just like in the warm-up. We're going to rearrange this to make v the subject. So combining these two logarithms together, we can do log of a divided by b, so we're writing it as a fraction now. Now we're going to make some room. Okay, dividing the 10 across the left-hand side gives us x over 10. Now we'll raise both sides to the power of e to get rid of the natural logarithm. So we have e to the x on 10 equals our fraction. Now rearranging to make v the subject, we're going to multiply the denominator across and divide the e to the x on 10 underneath here like this. These two guys just swap places. Now I'm going to subtract the 1 across, and while I'm doing that, I may as well write 1 over e to the x over 10. I'll bring it up the top by using a negative power. Now we just need to divide both sides by 10, and there we have our expression for velocity in terms of displacement. Okay, so a lot of work to be done, but most of it is fairly straightforward calculus and just some rearrangement. So as long as you're good with your integration and you're confident with rearranging logarithms, they're not too hard. The hard part is usually going from the question to an equation, which is the part that needs to take practice. Okay, on to example 2. This one is a vertical question. So we have throwing an object upwards with mass m and velocity v0. Air resistance at speed v is given by this expression here. K is a constant. We're going to have downwards as the positive direction. Okay, so we're throwing this one downwards. Usually the way in which we're moving is going to be positive. So we're starting from the top, down is positive. Show that this is an expression between t and velocity. All right, let's rip into it. Let's start off by writing our force equation once again. So force, we have gravity, and this time it's positive because we are moving downwards, and downwards is the positive direction, so gravity is working with us. However, like I said, resistance is always working against us, so the air resistance is negative. All right, there's our equation. Let's do some calculus. Let's write force as mass times acceleration. Let's divide both sides by maths, and while we're here, we may as well write the acceleration as dv on dt. Okay, I wrote it as dv on dt because looking at the target, we're trying to find a relationship between v and t, so not v and x. That's why I didn't use dv on dx times v. Okay, cool. We need to integrate with respect to v, so we need to invert both sides of the equation like this. Now we can integrate both sides with respect to v. So we get t on the left. On the right, again, we're using a logarithm, so we want the top to be the derivative of the bottom. The derivative of the bottom is negative k, so I'll put a negative k on the top, which means I'll put a negative 1 on k out the front, so I've really only multiplied by 1. Okay, now it's written in a form that we can do some calculus. Let's actually do our integration and use our natural log. So we get t equals negative 1 on k times natural log of the denominator, and then plus your constant as always. Okay, now we're here. Let's figure out the constants. So our initial conditions are at the start, initial velocity v naught is what we call it, v naught. Okay, so when t equals 0, v equals v naught. We'll sub that in. Looks like this. Moving this across to the left, we get this expression here is our constant when it's positive. Okay, that's our constant. Let's put it back up into our equation for t. Again, we'll write the positive part at the front because it looks a little bit nicer, but you don't have to if you don't want to. I'm not a cop, I'm just a maths YouTuber, wannabe maths YouTuber. Okay, now we're trying to get this expression, so we're just going to try and tidy up the right-hand side to make it look more like this. Combining our two logarithms together with a 1 over k at the front. Log of a minus b, once again, we can write as log of a over b. So combining them together as one fraction, and that right there is our target. You beauty. Moving on to part B. Now we've got that equation. We want to show that if we rearrange to make v the subject, it can be made to look like this. And from this, we're going to find our terminal velocity. So terminal velocity is your long-term velocity as t approaches infinity. So starting with what we gained in the last question, let's try and rearrange this. So let's multiply the k across the left-hand side. Let's raise both sides to the power of e to get rid of the natural logarithm. So we get e to the kt equals our fraction. Once again, multiplying the base across and then dividing the e to the kt across the other side. So these two guys are swapping places. Looks like this. Okay, now we'll once again bring the e to the kt up to the top by writing it as e to the negative kt. While I'm here, I may as well take away g from both sides to get minus g on the right. Now we are going to expand out these brackets, which looks like this. It's a bit of a mess, but we're getting closer towards this, which is also a bit of a mess. Now we just need to divide everything by negative k, and we'll have v by itself, and hopefully it can be made to look like this. So dividing by negative k, this is going to turn into positive g over k, which I'll write at the front. We're going to get a negative g on k here, and then this k is going to cancel out and become positive for this term right here. Now we can see all we've got to do is factorize the g over k out of these front two terms like this, and then what do you know? We have the target in the question. Beautiful. Now the question is find the terminal velocity. So we're looking at our equation and thinking about what's happening to our expression for v as t becomes a really, really big number. So in previous videos, I've talked about how e to the power of negative big number eventually goes towards 0. If you can't see why that is, jump into Desmos and chuck in y equals e to the negative x, and you'll see that the long-term trend towards the right is it goes towards 0. So the bigger the value of t is, the closer these two things are to 0. So if we're looking at a limit, we can just say, all right, let's make this 0, let's make this 0. which ends up 0 here, and g over k times 1, so we get a terminal velocity of g divided by k. Lovely. Okay, that's example 2 done. Let's go on with another horizontal question. Okay, example 3. I think I plagiarized this one from another trial paper. We've got a landing aeroplane, mass m, velocity v, 2 retarding forces. We've got a force of 4 mass newtons due to the reverse thrust of the engines, and we've got a braking force of mv squared over 40,000 newtons. Show that the equation of motion after landing is given by this. All right, let's jump into it. Let's make our force equation. So we're landing, which means where the plane is no longer moving forward. Well, it's moving forward, but it's not, it's not being forced forward anymore. So all we have acting against us is our resistive forces. We have our brake force just here, and we have our reverse thrust just here. Both of them acting against us, resisting our motion. Now we just need to try and make this look like this. So we'll write the force as mass times acceleration. We will divide everything by m to look like this, and then we'll write our acceleration as dv on dt as the question wants us to. Now combining these two fractions, we're going to write 4 as 160,000 divided by 40,000. And conveniently, 160,000 is 400 squared. So we can group these together as one fraction with a negative out the front. And we'll write 160k as 400 squared. And that is the target from the question. So we can now use this and answer the last two parts of the question. Part B, now that we have this, assume the airplane lands at a speed of capital U. Find an expression for the time it takes to come to rest. Okay, so we're trying to find a link between velocity and time. So obviously we're using our equation up here. We cannot integrate both sides with respect to t. So once again, we're going to have to invert this equation, take the reciprocal, and now that it's upside down, we can integrate both sides with respect to v. On the left, that'll get us t. On the right, we have an integral. So just like in the warm-up, we are looking at an inverse tan because we have something squared plus something on the bottom of our denominator, bottom of our fraction, sorry. So because we have 400 squared here, to use inverse tan, I would love there to be a 400 up here. That's why I've split the 40,000 into 400 times 100 and put the 100 at the front of the integral. Now this is in a good position to use inverse tan. So we have t equals negative 100 tan inverse of v over 400. Don't forget your constant on the end. Let's figure out our constant with our initial conditions. So when the plane lands, which is when t equals 0, the speed is capital U. So we have t equals 0, v equals capital U. Subbing that in, we get, if we put that across the left-hand side again, we get our constant is 100 tan inverse of u over 400. Putting that back into our equation over here, again, putting the positive part at the front, looks like this. And now we're trying to find an expression for the time for this to come to rest. So if you're at rest, that's when your velocity is equal to 0. So going to our equation here, letting velocity equal 0 means we're going to have 100 tan inverse of 0. This whole thing on the end is going to vanish, and we're going to get our final time right here. Okay, so subbing in 0, tan inverse of 0 is nothing, so the last term vanishes, and we get right here as our time taken to come to rest. 100 tan inverse of u divided by 400. Now for the final part, show that given sufficiently long runway, then no matter how fast its landing speed, it will always come to rest within 2.6 minutes after landing. Okay, let's go back to our time to come to rest from part B. All right, that's what we got from part B. What are we trying to find? We are trying to find when it will come to rest. So let's think about tan inverse. If you look up the graph of tan inverse on Desmos, or you might already have a good idea of what this looks like, we know that tan has a vertical asymptote at pi on 2, 90 degrees. That means tan inverse has a horizontal asymptote at pi on 2. So long term, as you scroll to the right on Desmos when you're looking at tan inverse x, it's never going to cross the line pi on 2. That's its long-term limit. That means no matter what u is, this whole thing inside tan inverse is never going to be more than pi on 2, which means that time is never going to be more than 100 times pi on 2. Conveniently, 100 times pi on 2 works out to be about 157, and because this was meters per second, our time must be seconds. And 157 seconds is conveniently about 2.6 minutes, so we've done what they asked us to do in the question. Okay, it doesn't matter how fast we land, as long as we've got enough room, it's going to take us 2.6 minutes to land, because that's what 100 times pi on 2 is. Okay, groovy. And looking at our final example for this lesson, it's an HSC question from 2017. It's 4 marks, so there's a bit of work to be done, but luckily the question has done a lot of work for you and given you a lot of the equation. So we've got particle projected upwards. So in example 2, we were being thrown down or being thrown up. Initial velocity, g is acceleration, k is a constant, v blah blah blah. The acceleration is given by this. So they've already done the work, they've made the force equation, they've divided by mass, and they've given you the equation right here to use. Particle reaches maximum height h before returning to the ground. It even tells you which expression to use, so they've given you heaps of tools here, you just got to be able to do the calculus. Show the maximum height is given by this. All right, let's dive in. So there's the equation they asked us to use. We're taking our acceleration from the question, writing acceleration as v dv on dx. Now we're trying to get from this to show that the maximum height is equal to this. That's why we are looking at an equation linking velocity and height. All right, dividing everything by v looks like this, dividing the right hand side. Now once again, we want to integrate with respect to v, so we're going to have to take the reciprocal of both sides. So we get dx on dv equals this nonsense. Now integrating with respect to v, on the left we're going to get x, and over here we're going to have v over g plus kv squared. We want to use a logarithm because the top is power of 1v, and we've got a power of 2 on the bottom. So we want to make the top look like the derivative of the bottom. The derivative of g plus kv squared is 2kv. So what I've done is I've put a 2k on the top of the fraction, and as always kept the balance by putting a 1 over 2k at the front, and don't forget you had a negative at the front as well. So here is our integral ready to go using natural logarithms. So we get x equals minus 1 on 2k, natural logarithm of the denominator plus the constant. Figuring out the constant, our initial conditions. Question said that initially we are thrown with velocity equal to this. So when x equals 0, which is when we're starting from being thrown, velocity is this. For our equation we need velocity squared, which is going to be a half squared, which is a quarter, and then squaring gets rid of the square root, so we get g over k. Okay, let's make some room and sub that in. So we have taking our equation just here, this line, and changing the v squared to be g over 4k looks like this. Okay, this works out pretty nice because the k's cancel out and we get g plus a quarter of g inside our logarithm. So we get 1g plus a quarter of g, which is 5 quarters of g. So that must be the value of our constant on the end of our expression. Again, I'm just going to write that at the front. And now here's our expression for our height in terms of our velocity. So we are trying to find the maximum height. The maximum height before you return to ground is the peak of your throw, which is where your velocity becomes 0 because you've reached the peak, you're no longer traveling up, you're now going to start traveling down. So to find the maximum height, just like in projectile motion, we're going to set the vertical velocity v equal to 0. So when x equals maximum height, velocity is nothing. Subbing that in, we get 1 over 2k times log of g on the end. Now we're just going to tidy these up by combining our two logarithms because they have the same fraction out the front. Once again, doing log of a divided by b. So we're going to have 5g on 4 over g. The fraction is going to sink down, so we're going to get 5g over 4g. The g's cancel out, and then what do you know? We get a maximum height of 1 over 2k times log of 5 over 4 as the question specified. So there you go. There's 4% of the 2017 HSC that required very little understanding of mechanics. We just needed to know how to integrate, rearrange, find constants, and then just, yeah, all the usual nonsense. Okay, cool. So now you're ready to go on and find some more HSC questions, do some practice. If you want some more practice from some textbooks, here are the horizontal and vertical resistant motion exercises from Howard's free textbook, or if you have Cambridge, 6D and 6E are also pretty good value. Okay, I hope that helped. Thank you for watching, and good luck for your HSC. I'll hopefully see you in the next video. Bye for now.